Welcome back, class, to section 17.8, entitled Precipitation, Q versus KSP. So similarly to what we were doing in chapter 15, we were looking at Q, a situation where there's a ratio of products and reactants when you are not at equilibrium quite yet. So we can use this value and compare it to K to predict which way the reaction would go. So if we want to look at this in the context of a dissolved compound, let's use sodium chloride as an example here. So let's have three situations here. Actually going to scroll down here. We'll start in the middle here. This is a saturated solution of NaCl. So remember, it's perfectly saturated. It's at the maximum amount of dissolved compound. That means we are at equilibrium. This is at equilibrium. So remember, if at equilibrium, Q is the ratio of products and reactants, and K is also equal to the ratio of products to reactants, remember that ratio is a constant at K, and so that means Q equals K. So this is kind of the middle area. At equilibrium, our Q value is going to be equal to our K value. Na plus Cl minus. The rate at which the aqueous and, solid. This is solid. There we go. This has reached K. There's a certain quantity of solid and a certain quantity of aqueous. So NaCl is forming precipitate in ions at the same rate. That's the definition of equilibrium. Now, what would happen if Q is less than K, specifically KSP? This is the point at which reaction should shift to the right. What does that mean in the context of this equation? If we are not at equilibrium yet, Q is less than K, that means we're going to be dissolving NaCl. So if I add to this beaker, for example, sodium fluoride aqueous and calcium chloride aqueous, and put them in here, I'm going to have a whole bunch of Na plus and Cl minus. I have to continue adding this to a certain point to get to a saturated solution. So at this point here, we're going to say Q is less than K. So at this point, we know reaction is going to shift right. Any amount of this stuff is going to stay dissolved. We're pushing to the right, just like we had equations before. Now, past equilibrium, the other side, Q is greater than KSP. At this point, I have excess solid here. Now it's a saturated solution on top. This is past saturated. And if I add Na plus and Cl minus ions to this solution, they are going to immediately precipitate out and fall down. So I have this solution over here of Na plus, F minus, Ca2 plus, Cl minus, and I add it to this solution. What I should actually witness is sodium chloride precipitating out of solution because we are past the saturated point. Over here, if I add that solution to this water, those will stay dissolved. So just like before when we're looking at chemical reactions or gaseous reactions, this relationship holds true. If I'm adding something to this beaker here, this is already saturated. I'm going to start forming NaCl right away, shifting to the right. Oh, I'm sorry, shifting to the left. Q is greater than K right now, so we're going to shift left back to sodium chloride. So that's really the main points here on the Q versus K relationship. And if we go down to example 17.22, actually I should probably write this out. This is selective precipitation. So sometimes you have a mixture of ions in solution, like this, barium and magnesium. And barium is very toxic. So how do we get that out of the water without selectively precipitate out of the water to get rid of it? Well, we can take advantage of other solutions. So if I add these two salts over here to the water, which one of these could selectively precipitate out barium? Well, let's think of each situation. So let's think about A. If I add sodium carbonate to water, what's going to put in there? We're going to put this and CO3 2-. And in here, I have a solution of barium and magnesium ions. Not sure what their counter ions are, doesn't really matter. So I'm adding this to here. So what are the compounds that could form? Sodium is not going to be involved, but the carbonate can add and form compounds with barium and magnesium. So let's just form these now. Barium carbonate or magnesium carbonate. What we need to do is look up KSP values for these compounds that we formed. So as in, which one is going to be, does carbonate give two compounds with very different KSPs? Or no? That's the question. Let's look at barium carbonates. I wrote table 17.2. This is the table that they tell you in the book to go look at. I have it pulled up right here. So this is in chapter 17.6, 2 sections ago. And barium carbonate, where are you? 2.58 times 10 to the negative ninth. Remember what this means. Small values mean very insoluble. So barium carbonate's a very insoluble compound, 10 to the negative ninth. Now let's look up magnesium carbonate. Let's see. 6.82 times 10 to the negative 6, top right there. So let's compare these. What this is saying is if I add carbonate ion to this solution, which is going to precipitate out more strongly or more selectively? Well, this one for sure, it's 3 orders of magnitude less soluble than magnesium carbonate. So this should work. I should be able to use a solution of sodium carbonate and selectively precipitate out the barium carbonate because of these really big differences. Whoops. Really large difference in the KSP values. So it looks like that would work. Okay, let's look at the sodium phosphate example. So B. Same thing, I'm going to add that to a solution of barium and magnesium. What are the two compounds that could form? Well, we're using the phosphate anion, PO4 3 minus. So I'm going to form barium phosphate and magnesium phosphate. Little mistake there. That should be a 2. And let's look up the KSP values for these. And I actually have these in front of me here. Barium phosphate has a KSP value of 3.40, check this out, times 10 to the negative 23rd. That's a pretty good indication that that would fall out of solution pretty easily. But what about magnesium phosphate? That's KSP value is 1.04 times 10 to the negative 24th. So these are only one magnitude off, one order of magnitude off. So we have to ask the question, are these different enough that this would precipitate out before this one? Or sorry, this one, this is smaller than this one, negative 24th. This is not a great situation. So you could try this and add phosphate to this, but a lot of this would precipitate out and a lot of this would also precipitate out. So we would rather use the carbonate species. Because of this 3 orders of magnitude difference, that's a massive amount of difference. If we added carbonate here, the barium carbonate would come out really much more strongly than magnesium. In this case, we would get a lot of magnesium phosphate coming out of solution with the barium. So that one wouldn't work as well. So that's how we can use a specific solution of ions to precipitate things out, just by using the KSP values. All right, I hope that made sense for you guys. Again, make sure, get back into this section, go through all the examples, and I'll see you in the next section.